Welcome to Math 104, Chapter 6.1 and 6.3. So these are done together because they flow really well into one another. So we are now going into higher degree polynomials, such as cubic functions and quartic functions. Now, cubic functions have the following structure of their equation. We have ax cubed plus bx squared plus cx plus d. Now, the graph of these, based on the leading coefficient here being a, if it is positive, these can look kind of like this S-shaped curve where it is steadily increasing, or if it's negative, they're going to be falling like this, very much like a positive straight line or a negative straight line. Now, cubic functions can have up to how many turning points? Well, if we recall from our graphing section, chapter 1.2, I believe, or 2.1, we said the number of turns is determined by the degree minus 1. So in our case, 3 minus 1 is equal to 2. So we can have up to 2 turning points. So if we were to graph something like that, it could look like this graph, or it could look like this graph. So lots of turns. We have 1, 2 turns for both of those graphs. Now, cubic graphs go in opposite directions. So we talked about this in that same section where we said your arms of your cubic graph go in opposite directions. They do not make that U shape like the other ones do. It says when leading coefficients are positive, so if we are working with a graph like this one here, right? If it's positive, then we are going to increase to the left. You're rising to the left, and then you're falling. You're falling to the left and rising to the left. Right. So sorry. So let's see if I were to draw that again. Of course, now I can't do it. There we go. So it says to the left, your graph is decreasing, and to the right, your graph is increasing. So we are going towards negative infinity or positive infinity. So we are falling and then rising to the right. Now it's opposite if we reverse your graph here. So on the left-hand side, we're actually going to go up towards positive infinities. So we're going up. I just wrote negative infinity, positive infinity. So we're rising to the left and falling to the right. Falling to the right. Sorry, what we're doing right now is discussing your end behavior. So where does your graph end up? Now, let's try it again with, actually, before I do that, let's try this example. It says graph f of x is equal to x cubed minus 8x squared plus 12x. Let's find the degree, the leading coefficient, the number of turns, whether you have a max or a min, your intercept, and let's place that in factored form. So lots of things that we can ask you. So degree is the highest power, which we can see clearly as 3, which means your leading coefficient here is 1. Now, number of turning points, at most it can have is 2, but let's see this visually on a graph. So add it to plus 12x. Okay, now let's figure out a good viewing window. Now, do we like this window? Not so much. We definitely want to see if we can get a little bit better, and I might just double check. There we go. So I actually did not type this in correctly. Let's get rid of that. There we go. Now that looks a little better. Our window still isn't all that great because we are missing an important feature on your graph. Now notice that we do need to get lower into lower to see your turning point. So that means your y-axis, your minimum value has to change. So let's try -20 and see how it looks. Now that's actually not so bad. So once you can see the really important features of your graph, then we can say it's a good window. So we are trying to figure out the number of turning points, which how many turning points can you see here? Well, we can see 2 turning points, and where are they located? Well, you have a maximum, a local max at 0.9 and let's just say 5. So number of turning points, 2. Your local maximum we said was 5 and 0.9, I believe. And let's try to find your local minimum. So here we have 4.4 and -17. So let's just do 1 decimal place. Now let's see if we can find any of your x-intercepts. So locating here your x-intercepts one more time on your graph, we have 0, 0, we have 2, 0, and we have 6, 0. So let's put that onto your graph right here. 0, 0, 2, 0, and 6, 0. Just want to double check that I have those values correct. Perfect. Now, one thing that it's going to ask for is perhaps factored form. So recall that back in chapter 3, we worked on trying to put your equations in different formats. In this case, one of the better formats to accomplish on both cubic and quartic is this factored form, which is just by taking your intercepts and putting them in an intercept form. So for starters, we're going to take all of your x values here, and we're going to say, well, this is x is equal to 0, that point. This one, x is equal to 2, and x is equal to 6. Now, in our previous lecture, we said if you know your x-intercepts, you can actually build an equation for this polynomial. So for example, if we have these x-intercepts, we can rewrite this equation in a different format. So if we could set all of these equal to 0, or not set them equal to 0, but get them onto the other side. So we can say, well, we're going to subtract 2 to the other side, subtract 6 to the other side. And this one, you guess you could subtract 0 to the other side, but it doesn't quite make sense. This is actually a very nice occurrence for us, and you're going to see why in a second. So we're just going to keep x here is equal to 0. X minus 2 is equal to 0, and x minus 6 is equal to 0. Now we are just going in the reverse direction of your factoring. So if we said, hey, this is fully solved, let's try and get it to be fully factored, your factored form. So right before this form, we said, well, before we set it equal to 0, we typically have things in parentheses. So we're going to put x minus 2 in parentheses, and x minus 6 also in parentheses. And we need this value to be in parentheses, but because it is only its value, so notice that around here we'll be putting its parentheses, your GCF doesn't really need parentheses, so it'll just go on the outside. We can set it equal to 0 if we'd want to show that it's fully solved. But even better, we're going to say it's equal to p of x. Just another way to say f of x or y equals, and that can be our equation. Now, before we completely say, hey, this is fully done, let's take a look at what your a is. So from the above, your a is equal to 1. It happens to be your leading coefficient. Now, before we round it out, we want to make sure that your A value gets stuck right in front of your GCF if you have one, or any sort of parentheses. So this is equal to A from the above. Now let's see if we put this into your calculator and if it transforms your graph onto the original one. So y equals, we have 1x times, let's see, we said x minus 2 and x minus 6. And notice it went from a green graph onto a, I think, purple. So this is the exact same graph, just written in a different form. And we could also have done this algebraically as well, from going to this expanded form into a factored form. So in order to do that, let's take a look at x cubed minus, what was it, 12, 8? 8x plus 12, I think that's what it was, 8x squared. Okay, so can we factor this? Well, I haven't tried factoring something with a degree of 3 before, but what do you notice about all of your values? Well, they all have an x in common. So at the very least, let's factor out an x. Oops. We change each degree on your x by just 1, or we just take it away completely. Now, can we factor the inside of the parentheses? I just want to verify that I wrote it correctly. Yeah. Yes, we can. So let's transform, or let's figure out your factors of 12. Let's see, 6 and 3 and 4. Now, of these, which one can get us to a -8? Well, 2 and 6 can, as long as we arrange it as a -2 minus a 6, so that when we go to multiply it, we get to positive 12. So we have x, we have x minus 2, and x minus 6. And wouldn't you know, isn't that the exact same equation that we have over here? So let's try it again, but now with a quartic function. Now, quartic functions, the only difference between quartic and cubic is now we're changing a degree, and we can have another term tacked on to the end. Now, these graphs are more of a wave or a U-shaped graph. Now, if A is greater than 1, so if this A is positive, we're going to be working with a U shape. Now, this can be a U, or if we have many, many curves, it can be kind of a W shape. Now, if it is negative, we're working with an upside down U, or kind of a wonky W shape just facing down. So, how many turning points can we have? Well, if we take our degree and subtract 1, we can have 3 turning points. At most, 3 turning points. And you can see that here we can have at most 1, 2, 3, 1, 2, 3. And keep in mind that is at most. Notice here we only have 1, and that is okay. Now, quartic graphs go in the same direction. So the end behavior goes in the same direction. So all of these arrows point together. So therefore, when the leading coefficient is positive, so if we have something like, this, if it's positive, so going from the left is going up, it's rising. And because they go in the same direction, also to the right, we are rising. And if we were to do it again, but with a negative leading coefficient, then we are not rising, but we are falling for both. So pause the video, see if you can tackle this next portion. All right, degree. Degree is a 4, leading coefficient is a -1. The number of turning points. Let's take a look if we were to put it on a graph. Y equals negative x to the 4th. Let's see, minus x. Oh. Plus 6. Okay, so this is what our graph looks like. Let's change your window. So we definitely need to go up a little bit further. So let's change this to maybe be 20. And actually, that's not a bad graph. So we're going to keep this window. So your window, with your window, we can clearly see the important bits of your graph. And if we are asked to find your maxes and mins, we have several maxes and mins. Now let's take a look at your minimum. Your local minimum here is at 0, 0. Now let's find one of your absolute maximum. It is also considered your local max as well. This is occurring at 2.1, or yeah, let's say 2.1. And your other one is at -1.4. Okay, number of turns we saw was 3. We said local minimum was at 0. Oh no, not add a comment. Oh, how do I get out of there? Okay. We had a 0.00 for your minimum. Let's also do a local max and absolute max. That would have been 2, 1. Okay, and one that was just the local max was at -1.4 and 7. Oh no, 5, 2, 5, 2. And there you have it. Now let's take a look at your x-intercepts and see if we can build it into a factored form. So let's X out of there. One more time, click. You have a few x-intercepts showing at -2, 0, and 3. So see if you can get it into factored form. So first thing we said was get everything set equal to those x values. So getting these x values to appear right here. We said from here, let's add or subtract to the other side. So let's add 2. Or you can say, if you're ready for it, you can just put it into parentheses if you want to make that jump. X plus 2 is 0. We said we can't really do much when x is 0. 3 is 0. And then from here, let's put it into parentheses. And just x. So we can say p of x, or f of x, or y is x, x plus 2, and x minus 3. Now the last thing we need to make sure is to verify what your leading coefficient is. A is -1, so we are going to use that as a part of our answer. So in here, we're just going to insert a -1. And let's see how that looks on your graph. So down below, we have y equals, we have -1 x, x minus, what is that, 3. I think I messed up the signs. X plus 2. Oh, I must have messed up. Hold on. Oh, actually, I did mess up, but not in the way that I thought. Let's take a look at your graph one more time. Let's X that out. Now, one thing we haven't covered, but is actually on the next page, which I completely forgot to look up at my notes, is what is looking like it's happening at your x-intercept of 0, 0. Well, unlike your other x-intercepts, notice that the other two at -2 and at +3, they go right through the x-axis, whereas this one, it actually is bouncing. It's not going through, which means it makes it extra special. So if you notice that your x-intercept is bouncing off the x-axis, then this actually has a special degree. This has a degree of 2. Now I'm going to write, let's see, I think on the next page it explains it a little bit more as to why it is. Oh, there's actually a mistake on the page. I must not have put the next page in there. So one thing that I will hone in on is if you see a bounce on the x-axis, this multiplicity here has a degree of 2. If you see something that passes right through the x-axis, that has a degree of 1, which is what ours have here. Our degrees of 1 we saw pass right through your x-axis. And last case, you might not see it as often, is if your graph slides through the x-axis, then it has a degree of 3. So with ours having some sort of a bounce, this x, where it happens on, we said it happens at 0, 0. We now are going to give that one a degree of 2. If it happened on where we had x squared, or sorry, a -2x, that means that this one can change its degree to 2. The most you see is usually 1 and 2. You may see a degree of 3 if it's a little unusual case, but you're looking for some sort of a slide through the x-axis. And I'll label these as your x-axis. My apologies, I thought I uploaded the correct notes. So if we change that, so we go from, and I'll show you that mistake, how I caught it so quickly. So we said we had negative x plus 2, and x plus, oops, x minus 3. So not only is your graph not doing that certain behavior, while we still have the correct x-intercepts, we need to transform this one to have now a squared on it. And notice that it is giving that nice bounce look to it. Now let's clear out this one in black and let's change it so you guys can see what it might look like when there is no, not a bounce on the 0, but instead on the 2. So by changing your multiplicity of a 2, notice that it then bounces on your -2 area. And let's see if it'll work. Let's say this one, I want a multiplicity of a 3. Notice that then it starts to slide through the one that has your 0, 0. So just by changing that multiplicity to 3, it now is acting as a slide. So this one right here, 3, 0, has a multiplicity of 1. So you can see clearly it's passing straight through. 0, 0, it's doing that little slide, and -2, 0 has that bounce shape. Now let's take a look at an example. It says the daily revenue from the sale of the product is given by R equals this equation. in dollars, where X is the number of units sold. So graph on a window, and they're giving us the window. This is a very, very large Y window. So be super careful to keep track of all of those zeros. You might want to consider changing your the steps, the scale. And we want to know what is the maximum daily revenue. And then we also want to know the interval of X that it is increasing. Six X cubed. And I just realized I made a mistake. We'll go back in a second once I finish out. That's cute. Okay, I just wanted to verify that these are all correct. I don't know why I put it out of order. Also, the world's worst memory. There we go. Okay. Now, before I continue, I do want to back up just a moment because we talked about how to factor it here on this last example, but I never got around to talk about how to factor this one. So this one is actually factored the exact same way as the previous one. Let me throw that over there. Negative x to the fourth. Something x squared, isn't it? 6. Okay, so let's try and factor this one first by taking out a GCF. So we should be taking out an x squared, and because it's very hard to factor with a negative coefficient out front, let's also take out a negative. That'll leave us with x squared plus x plus 6, which then we can factor 6. Oh, actually, notice that. Man, I'm making mistakes all over the place. We now have to change your signs because we did factor out a negative. So that means all of these values will change. So now we can go ahead and try and factor the inside. So we're looking at 6. So 1 and 6, 2 and 3, of which 2 and 3 is going to work as long as you have a negative 3 and a positive 2. We can also double check by multiplying these to get a negative 6 and then subtracting these to get a negative 1. So notice that that is the exact factored form that you have over here. So that checks out. Now on to finally this example. So we are looking at the maximum profit, and we are given a window here. So it says we want to go from 0 to 170, and again from 0 to 12. There we go. So that is a nice curve, and this is the graph that, or the window that we'd like. Now they are asking at what is the maximum revenue. Well, we have 90 and 97 to 100. Now, if you are curious as to what the scale might be, perhaps you're doing this on a TI-84, just look at the values between 0 and 170. If it's a pretty wide range, then we can be perhaps at like 5s or so, not so bad. Or your Y values, if it's a huge range, so the difference between 100,000 and 0 is pretty large, so we can actually get a lot more generous with it. Perhaps you go up by 1,000s, by 2,000, so maybe perhaps by 2,000. And it doesn't change so much on Desmos, but perhaps on your graphing calculator it will. I already forgot our point. 90. Okay, So this being our point, I'll make this a little comma. So this is our point. So when it says, what is the maximum daily profit revenue? Well, which one is going to be the revenue? Well, this is going to be your revenue, and this is going to be the units sold. So can you bring meaning to your work? Well, we could say the maximum possible daily revenue is achieved by selling 90 units to get a revenue of $9,200. So something like that to bring meaning to your work. Then it says, over what interval of X value is the revenue increasing from 0 inclusive? So looking at your graph, we want to determine where's your graph rising, increasing. So we are increasing from your 0 value here all the way up. Notice that your graph is rising, your X values are rising all the way up until we get to your max. And then we start to fall. Now your max is neither a rise nor a fall, so we're not going to be including this value, but we will go all the way from your 0 starting point. So from 0 inclusive, we have that equals to sign, so we're going to include 0 and go all the way up to 90, non-inclusive. And just to demonstrate that on the graph right over here. So if we go from 0 and then back down, we're only looking at this portion of the graph right here. So from 0 to 90. That's when it would be rising. Whereas if we're talking about your revenue decreasing, it would be the opposite, and we would get whatever this value would be. So now let's take a look at your factored form. So if you have some information where they're telling you what A is right over here, and they're giving you some sort of graph, can you make an equation? Well, we determined from your following equations over here that as long as you have your x-intercepts, we can in fact make an equation. So our equation here is formed from your x-intercepts. So pause the video, locate your x-intercepts. We have 3 x-intercepts here. So we have when x is equal to -2, when x is equal to 2, and x is equal to 2 here. I'm so sorry. I looked at a 2 and I say a 2. There you go. So just like the times before, we're going to add this 2 to the other side, subtract it here, leave your x is equal to 0 alone, and then stick it into parentheses. So bringing it all together, we can have p of x is equal to, leave space for your a, x, your GCF, x minus 2, and an x plus 2. Those are right from your x-intercepts. Now let's take a look at your factored, your a. They're telling us that a is equal to 1, so we can substitute that right in. And then we also need to take a look at your direction. Ours is increasing, which means a, is that going to be positive or negative? Well, it's increasing, so we're going to stick with a positive 1. We can certainly graph that on this graph here. Let's make sure that that doesn't look so strange. Okay, let's go and graph. Y equals, we said 1x, x plus 2, and x minus 2. Now, is that the same graph? I believe so. We can verify as well by how close our maxes and mins look, which looks pretty good to me. Yeah, just off by a little bit. There you go. So let's try it again over here. Be careful on this one. You have your x-intercepts here, which are at -1, 1, and 0. Now be super careful on this one. Is there something, or what is the difference between these graphs, other than perhaps one is a cubic and one is a quartic? Well, this one has that bounce factor. So we need to make sure that this now has a degree of 2 because it bounces on the x-axis. So once we add some of these things over, or if you're ready to stick them into parentheses, and we put them all together, leaving room for your a, we have x squared for your bounce, x plus 1, x minus 1, and then let's take a look at your a. They're telling us a is 2, and what about your direction of the graph? Well, the direction is falling, right? We're concave down, so that means ours has to be negative. Now let's go ahead and see if that goes on to your graph. Y equals -2x squared, x plus 1, and x minus 1. Now, does that look pretty close? I would say so. There we go. Yes, that looks pretty good to me. Because your maxes look spot on. So let's round it out as well to now just work on a little bit of factoring when it comes to some of these higher ordered values. So in this case, just as we had seen in our previous example, let's take a look at any sort of GCFs. So GCF here being an x squared, and let's reduce all of these degrees by 2. And get rid of them all together. Now we can see if we can factor normally. So 18, 1 and 18, 2 and 9, 3 and 6, which we're trying to achieve a -3. So let's take a look at 3 and 6. 3 would have to be positive, 6 would be negative to make a -3. But when multiplying, we're going to still get a -18. So x squared, x plus 3, and x minus 6. That would be your factored form. We'll move that down a little bit. Okay, let's try it again. A little bit more GCF. We take out a -x squared to get x squared plus 16. And I wonder if I made a mistake on this one. I think I did. I think I wanted to change it up. Can we change this one to a positive for me? You would still want to perhaps change, what was I just going to say? We still want to be able to recognize what's going to be happening here. We also still want to factor out this negative because it is harder to factor when your leading term is negative. So taking it out, changing your signs, we get factoring out the second term. Because this is now a difference of squares, this is x to the 4th, we can have x minus 2 and x plus 2. This would be considered fully factored. It also exposes how many x-intercepts that you have right off the bat. Now, what is going to be happening here when x squared is present? Well, this one would be a bounce. So you'll see it bouncing off of the axis. Now, last one, this one is a little special. We have seen something like this in a way. When we were doing your complex factoring, we had to do factor by grouping. So in our case, let's factor by grouping right off the bat, as long as there's no GCF on all four terms. Since they're not, we can continue. So let's factor by grouping. From the first two, we can take out an x squared. You have to make sure you're leaving a placeholder of -1. Otherwise, when you go to distribute, it might not work and look the exact same if you don't leave behind the 1. Doing it again, notice that this one has a negative and this one is positive, so be super careful on your sign changes. So we're going to be factoring out a -4 to make a positive 3x minus 1. Let's say you did not take out a negative, instead you did a positive. That just changes your signs here, which notice how close these two values are. We just need your signs to match, which then factoring out the negative. I just realized I made a mistake. I need to stop making videos today. So now we have x squared minus 4 and 3x minus 1. Now, what is this one called? This one is called your difference of squared. So 4 squared is another way to say 2 squared, which then we can break down a little bit further, which if you now realize I made my mistake, please go back and fix it. Now, what would we fix it to? Notice I wrote 4 squared and I wrote down 2's. Just having too many 2's. These should be changed to 4's. You could also have done this graphically too by finding those x values and then placing them into an equation.